Less than 1% of Earth's water is drinkable. The rest, 360 million cubic miles, is salt. 2 billion people on this planet cannot access clean, safe water. By 2030, global demand will exceed supply by 40%. Aquifers that took millennia to fill are being drained faster than they recharge. We have known if this crisis was coming, we just couldn't solve it. Now, a single material may change everything. Hit subscribe because the way humanity drinks water is about to change forever.
For most of human history, fresh water was simple. You found it or you died. Rivers, lakes, and rainfall fed civilizations for thousands of years. Every great city was built near fresh water. But population growth changed the equation permanently. Demand began outpacing what rivers, lakes, and rainfall could provide. Engineers looked at the ocean. 97% of all water on Earth was sitting right there. The problem was the salt. Seawater contains roughly 35 grams of dissolved salt per liter of water. Drink it and your kidneys are overwhelmed. They cannot excrete salt fast enough and begin to shut down. Early desalination was thermal. Engineers boiled seawater, captured the rising steam, and collected what condensed back as fresh water. It worked, but the energy cost was staggering, 20 kilowatt hours to produce just 1 cubic meter of water. Then came reverse osmosis. Seawater forced at enormous pressure through a dense polymer membrane, just like a molecular sieve. Salt ions are too large to squeeze through the membrane's tiny pores. Fresh water passes. Salt stays behind. Reverse osmosis transformed desalination. Energy consumption collapsed from 20 kilowatt hours down to just 2.5 per cubic meter. Today, over 100 million people depend on desalinated water to survive, every single day without exception. But reverse osmosis has a hard ceiling. Polymer membranes foul with contaminants, degrade over time, and cannot push much further. The theoretical minimum energy for desalination is 1 kilowatt hour per cubic meter. We are still 2.5 times above it. Closing that gap means finding a fundamentally different material, something that doesn't play by the same rules as polymer. That material already existed. It had been sitting in a laboratory in Manchester since 2004.
Graphene was first isolated in 2004 by 2 scientists at the University of Manchester. Andrei Geim and Konstantin Novoselov used adhesive tape to peel single-atom-thick sheets from ordinary graphite. The result was a material 1 atom thick, the thinnest substance ever isolated by human hands. 6 years later, they won the Nobel Prize in Physics for that single discovery. Graphene is a single layer of carbon atoms arranged in a perfect repeating hexagonal lattice structure. That hexagonal structure gives graphene extraordinary mechanical strength, 200 times stronger than steel at a fraction of the weight. But strength was not what attracted water scientists. It was graphene's relationship with water that mattered. Because graphene is just 1 atom thick, water molecules face almost zero resistance flowing through its channels. Researchers at Manchester demonstrated that water moves through graphene oxide membranes essentially frictionlessly via 2-dimensional capillary channels. Computer simulations showed graphene membranes could move water up to 100 times faster than conventional reverse osmosis membranes. Faster water flow means lower operating pressure. Lower pressure means dramatically less energy consumed per cubic meter produced. The key engineering challenge was controlling the spacing between graphene layers. Too wide and salt passes straight through. Manchester researchers solved this by physically confining the graphene oxide layers and achieved 97% rejection of sodium chloride. Separate laboratory tests under specific optimized conditions pushed salt rejection even further, reaching 99.9%. Graphene does not brute force water through like polymer membranes do. It guides water at the molecular level. This is molecular precision operating at an atomic scale, and it changes everything about what is possible.
Chennai, India, 2019. A city of 10 million people ran almost completely out of water. The four main reservoirs supplying the city dropped to nearly zero. Tanker trucks became the only lifeline. Hotels closed entire floors. Restaurants shut down. Offices sent workers home. A modern city grinding to a halt. Chennai is not an isolated case. It is a preview of what is coming globally. Cape Town nearly became the first major city in modern history to completely exhaust its water supply. Day zero, the day taps would run dry across the entire city, nearly arrived in 2018. Residents were restricted to 50 liters per person per day, less water than a single standard bath uses. Both cities averted full collapse through emergency rationing, but the underlying crisis was not solved, just postponed. The World Bank now reports the world is losing 324 billion cubic meters of fresh water annually. That is enough water to meet the needs of 280 million people every single year. Groundwater reserves that took thousands of years to accumulate are being drained in decades by agriculture and industry. The communities bearing the heaviest burden are not the ones driving the consumption. They never were. Every 2 minutes, a child dies from a disease directly linked to unsafe or contaminated drinking water. Women and girls in water-scarce regions spend an estimated 200 million hours collecting water every single day. The ocean sits beside all of this. 360 million cubic miles of water, almost entirely unreachable, unless we find a way to take the salt out, cheaply, at scale, everywhere. The numbers behind graphene membrane research are not theoretical promises. They are published, peer-reviewed, and verified. In 2017, the University of Manchester published a landmark result in Nature Nanotechnology that changed everything. By physically confining graphene oxide layers, they achieved precise control over spacing between individual atomic sheets. The result was 97% rejection of sodium chloride, at the time an extraordinary laboratory achievement. Separate graphene oxide membranes on polymer supports achieved 99.9% salt rejection under optimized conditions. Water flux through graphene capillaries was measured at rates orders of magnitude above commercial reverse osmosis membranes. Simulations by Cohen-Tanugi and Grossman at MIT showed tripling membrane permeability could cut energy consumption by up to 46%. That would push desalination energy costs toward the theoretical minimum of 1 kilowatt-hour per cubic meter. For context, current best-in-class reverse osmosis plants still consume 2.5 kilowatt-hours per cubic meter. Graphene membranes also resist fouling far better than polymer alternatives. Contaminants struggle to bond to the atomic surface. Fouling is one of the biggest operational costs in conventional desalination. Membranes clog, degrade, and must be replaced regularly. Graphene oxide is also chemically stable under chlorine exposure, something conventional polymer membranes degrade rapidly under. The EU-funded Aquasol project launched in 2025, with Professor Raoul Nair at Manchester leading graphene membrane development. The project's goal is to increase membrane durability and reduce energy demands in real-world desalination conditions. 7 partner institutions across 6 countries are working together to move graphene membranes from laboratory to pilot scale. The data is compelling. The trajectory is clear. What remains is the hardest part of all: scale. Here is the honest truth about graphene membranes. The laboratory results are extraordinary. The real world is harder. Producing graphene sheets that are completely free of microscopic defects at industrial scale remains an unsolved problem. A single microscopic tear in a graphene membrane allows salts to bypass the filtration entirely. The whole system fails. Manufacturing defect-free graphene at the scale needed for a desalination plant is a different challenge entirely. Cost is the second barrier. Graphene production costs have fallen significantly, but still exceed conventional polymer membrane materials. Long-term durability in real seawater conditions has not yet been proven at anything approaching commercial scale.
Seawater is not a controlled laboratory environment. It contains biological matter, sediment, microorganisms, and chemical compounds that attack membranes. Retrofitting existing desalination infrastructure to accept graphene membranes requires significant engineering work beyond just swapping the membrane material. These are real obstacles, but every transformative technology in history faced the same gap between laboratory and industry. Reverse osmosis itself took decades to move from laboratory concept to the dominant global desalination technology it is today. The question is not whether graphene membranes will reach commercial scale. The question is how long it takes. There is also a geopolitical dimension to this technology that rarely gets discussed in the scientific literature. Nations that control advanced desalination technology will hold enormous strategic power in a water-scarce world. Water is the new oil. Countries already facing extreme water stress, parts of the Middle East, North Africa, South Asia, cannot wait decades. For those communities, affordable, scalable desalination is not a technological curiosity, it is an existential necessity arriving right now. There's also the question of who benefits when this technology finally reaches commercial scale deployment. If graphene desalination remains locked behind high costs and patent walls, the communities that need it most get left behind. Open research frameworks and international collaboration will determine whether this technology serves humanity or just the highest bidder. The environmental picture adds another layer. Desalination produces concentrated brine that must be carefully managed and disposed of. Discharged carelessly, brine devastates marine ecosystems. Saltier water near discharge points kills species that cannot tolerate the change. Graphene membranes operating at lower pressure would reduce brine concentration compared to conventional high-pressure reverse osmosis systems, but brine management must be part of any serious graphene desalination deployment from the very beginning. Paired with renewable energy sources, solar and particular, graphene desalination could become genuinely carbon neutral at scale. The Middle East already produces desalinated water at record low costs using cheap solar energy as the power source. Add graphene membranes to solar-powered plants, and the cost and energy equation shifts in ways that matter enormously. We are at the beginning of this story, not the end, not even close to the middle, but the direction of travel is clear. Graphene membranes are moving from laboratories into the real world right now. The water crisis is not waiting, and for the first time in history, neither is the solution.
Graphene was discovered with adhesive tape in a university lab. What it unlocks could feed a planet. 2 billion people are waiting for a solution that science has already begun to build for them. The laboratory results are real. The momentum is real. The challenge of scaling it is equally real. But humanity has solved hard problems before, and the stakes have rarely been higher than this. The water crisis just met its match. Hit like, share this with someone, and subscribe to SynthCosmos. We cover the science reshaping our world as we know it every single week. We'll see you in the next one.